two-body problems, we have a conservations of the momentum, conservations of the mechanical energy, and conservations of the eccentricity. So today I'm going to show this one. And because we are recording, I like to use the central space here. So here is the integral of the two-body. So here we have three conservations. The first one is the angular momentum. And here I give you a summary of what we're going to develop today. And so all the notations will be explored today. And the second one is the eccentricity. And by definition, E equal to 1 over mu and V H minus mu R. The third one is mechanical energy. So here the R is the radial. Let me use graph to show it. So this is the main focus, for example, the center of the Earth. Or one focus of the elliptic orbit. So this is R, the vector R, and to here we have the in tangent direction, this is velocity V. Okay, so this is tangent to that directions. And so the magnitude of this is R, the magnitude of the V is V, so that is the notation we use here. And H simply is the derived quantity per this definition. E is a derived quantity per these calculations. And E is the specific. So here, if otherwise we don't specify the emphasize, then everything here is specific. And the same thing specific. Specific, that means the quantity per unit mass. Okay, so that is the definition here. So that is the quantity we're using those things. Today we're going to explore this. And how to obtain the conservation of the angular momentums. And here from our equation of the orbit. Is this R double dot plus mu R cubed R equal to 0. So this is our equation of the orbit. We're starting from here. So let me call this is equation 1. And the first one we're going to talk about is the conservations of the angular momentum. And again, if otherwise specified, then here always we indicate is a specific angular momentum. Okay. So this one is simply this. We simply take R cross product with equation 1, and this one equation 1 equal to 0. So this one should be equal to 0. Based upon this, we can do little manipulations. Equation 1 is R double dot plus mu. And right now we're still in chapter 1 of the textbook. And again, the textbook also have the detailed derivations like this one. But again, a textbook being written is very concisely. So here I try to get more information for you to follow up. Okay, right now for this one, then we can expand it. So from this equation here, we individually deal with, so for the first term, R in the product, cross product with R double dot. This one we can do is this. R double dot is the derivative of this one. Okay, and this one basically is R cross and V, because the accelerations of the radial we can describe as this one. So this one is equal to, again, you can verify dt R dot V. Okay. Why? Because here you can do the very quick side calculation. This one, if you take the chain rule, basically that is R dot d dt V plus dr dt times this one. This term is V. So basically the one cross product itself equal to 0. So that's the reason here this term equal to this one. And the other one, the second term is R dot mu R3 R dot. So again, that is the cross product of itself. So this one equal to 0. Okay. So therefore, this equation basically we have is this d dt R cross V equal to 0. So time derivative of certain quantity, certain vector equal to 0. That is our definition of H. So here we are given the vectors, location vectors of the say satellites here, and we know the vectors. So you simply take the cross product of RV, then that will give you the momentum, and that momentum. Okay, so this is called the angular momentum, specific angular momentum. And for calculations, say for example, if you would take up in the Cartesian coordinate systems, you can try is this, and this is a unit vectors ijk in the Cartesian coordinate systems. Then R, for example, you have the coordinates rx, ry, rz, and v, for example, you have vx, vy, and vz. Then you can take these manipulations to find the three components. So say hx and hy and hz in three directions. Okay, so here is say for Cartesian. For example. Okay. So that is the angular momentum, and this one equal to constant, because the derivative of h equal to 0, so this should be constant. The constant, that means conservative over time. And here we have more information. We're going to introduce a new term. So say, let me redraw the orbits again. So here, this is the focus. This is the orbit. Say this is the location of the satellite. So here is our R. So connecting to this is the radial directions. So this is our R here. And I begin to laugh. This is not good for demonstration. I will keep it. Let me draw another one. So in this way. Let me make another scenario that will be better for demonstrating of this concept here, and then I will go back to you with these figures. Okay. So, for example, here we consider it a satellite to Earth. Okay, that is the radial direction here. And this is the in tangent directions, that is the velocity v we defined. Okay, and now I want to introduce new terms. So here normal to the radial directions where the satellite is, I draw a vertical line. So basically, this indicating is the vertical directions to normal direction to R. So here is the normal direction. This one is specific. Again, that is the locally. Locally, that means at this moment satellites locate. Local to the current direction, we make a vertical line, and that is normal to the vertical, the radial direction. This is we call the local horizon. Horizontal. And local horizontal line or local horizon. Okay. And with this line be defined, then we can define a term. This term is very, very important. We measure from the local horizon to the directions of the velocity, that angle. And in our textbook, we're using phi. The phi is called the flight path angle. And sometimes people call this is called the leading angle. Leading angle was term used in other textbook, and in our textbook we use is a flight path angle. And flight path angle, again, that is the angle between measures from the local horizon to where the velocity, directional velocity. For this demonstration, again, we take the this direction, which direction? Clockwise direction is a positive. So let me back to here, and so say this is, let me make it, so here is the local horizon. And this is the velocity. Okay, so again, by definition, the angle we measured is from here to here, that is phi. And compared to this one, this is a positive angle, this is a negative angle. Okay? So we didn't waste this drawing. Basically, I show you the two things here. And on the other side, I don't know why, the textbook also used a different, another notation. Basically, the measure here is called the gamma. And gamma basically has no specific definitions. And so here, for example, based upon the phi or alpha, so here the magnitude, let me continue here. So therefore, the magnitude of the angular momentum equal to the magnitude of h. And that one simply can be, because h is the cross product of r v, so that one we're looking at here, that is r times v times the, excuse me, cosine phi. Okay, and how can we do it? How can we achieve this one? So probably I can show you the calculation again. Calculation, let me repeat this one. So we can use this one. So say, for example, here, let me label my coordinate system. This is x coordinate system, this is y coordinate system. Okay, I pick this local coordinate systems. So h equal to I, j, k, the local coordinate system. The first one is the coordinates of the radius, so that is r, 0, 0. So r is in the I direction, here a line in the radial direction. And v is, in terms of the local coordinate system, v have components here, is v sine phi and v cosine phi 0. Can you see it? Okay, you simply project the v. So here this is the x and y coordinate systems, and here this is our v. So here this angle is the phi. So you can see the projection of the v onto the xy coordinate system. This one is y component. Y component has the v sine phi, right? And this is the y component which has a v cosine phi here. Okay? So we implement this one basically here, that has I, and we multiply this one is 0, and we have j. J is 0, and we have k. K is r v cosine. Okay? So you can see here we also saying the direction of the h is out of plane, which means normal to the orbital plane. And the magnitude is given by this. So that is the calculation for this one. And again here, because in our textbook, it also uses gamma. So if you have to calculate in terms of gamma, that is simply is RV times sine gamma, because v plus gamma equal to 90 degrees. So cosine phi equal to sine gamma. We simply use this exchange. So here is the, we have the notes. The first one, the magnitude is equal to this in terms of the displacement, magnitude, the speed, and the flight path angle. We can calculate by this. Then the second one, from this calculation, we indicate h determine the orientation of the orbital plane. Orientations of the okay, so in our drawing on whiteboard, I can only show is in this whiteboard plane. But in general, say this is the orbital, say this is the orbit like this one. So orbital plane can be in this orientation, or orbital plane can be inclined in these orientations, or inclined in that orientations. So in 3D, how can you determine this orientation? Again, simply you define your coordinate systems, the artificial coordinate, the inertial coordinate systems, and then you interpret your r vector and v vectors in terms of that coordinate systems. Then you can determine the orientations. And simply, again, using this kind of single term calculation, you should be able to determine that vectors and also the magnitude. Okay.